So hopefully this works. I'm gonna do a little bit more discussion of Lab Exercise 4 to help you guys out. So we're kind of, we're familiar with all the different aspects of the lab exercise, like this finite state machine, the PWM, the encoder from last time. But I've updated a few things. I've managed to make, there have been a few updates, but I've managed to make it so that all the logic is as was presented previously, with only a couple small additions. So just wanted to walk through, highlight those, give you a little bit more guidance on how to do a couple of the things I ask of you, and yeah, let you guys go do your thing. I'm confident you guys will do well. So none of this has changed. The PWM is still being done in the same way. We're calling it not run due to some hardware changes. Wow, it's windy out there. Due to some hardware changes, I had to reverse the logic a little bit, but I was able to do that without too much trouble, so I just put in a little not gate. We'll talk more about gates next week, but I could just reverse the logic from what our amplifier was expecting was a run channel instead of a not run channel. So now ours is congruent with what we discussed last time, and it is looking for a not run. So everything is the same here. Nothing's changed. Similarly with the encoder, I only have, unfortunately, 2 encoder cables. I had to solder them myself. It was not fun. A couple of you were in there, so you know. But they are working, so they're on lab stations 2 and 3, so those are the ones that have the encoder working. You can debug everything else before trying them, and then go ahead and try those 2 lab stations to do the actual debugging. This is all. What I did though is I added something to channel 1 and to channel 2, and that's because our amplifier has a direction aspect to it. So the PWM on channel 0 is one aspect, but then if you want to go the other direction, you have to switch. So if one was high and 2 was low, and you're going one direction, if you want to switch directions, you would flip 1 to low and 2 to high, and that would signal to our amplifier that you need to reverse direction. So I added that aspect, and you're going to find that a little later on. I'll show you where I put the description of how to put it in the code. But you only need to put it in once. It doesn't need to be in the loop every time. It just needs to be in the loop, or it just needs to be before the loop where you go through your different state functions. So nothing here has changed. Encoder, reading the encoder. So the main lab is all the same. And all of these state transitions are the same that they were before, so nothing's changed there. So I did a lot of work in the background to try to make it so that nothing really changed from our last description. And so all this is as it was before. Under functions, we still use our double in, initialize SM. And I put a little bit, I changed this initialize SM description just slightly to try to make it a little bit more clear for those of you who've brought some issues to me. So first of all, I misspoke when I first presented this. These DIO A70 DIR, for instance, these variables here. So they're coming from this. They show up explicitly in the NIFPGA MyRio 1900 FPGA 30 header file and then the MyRio 1900 header file. And they're there to specify which register addresses are written to for telling the different digital I/O pins on a given connector, which register to write to access each of those. So when you initialize them, you need to use the corresponding variable that are defined in these header files. So if you're going to use the DIO on connector A, so connector A is specified by that A. 7.0 is specifying that you're going to be using the bank of DIO inputs and outputs between 0 and 7. So I explicitly put in a little comment here. From 0 to 7, if you're going to use 0 to 7, you're good with using this one. If you wanted to use 15, or if you wanted to use 8 through 15, you'd have to use a slightly different one. And actually I have a little example here in the footnote of what you needed to do if you had 8 or 15 down to 8 as your pins. So I give a little bit more explanation in this footnote here, and I think that should help clarify things. It was just an accident that the 7 in the fact that we were using as an example channel 7 last time corresponded to this 7. It's actually 6 and 7 have the same look, except for you say CH6 or CH7, and when you set the bit for that structure, you set it to 6 for channel 6, 7 for channel 7, etc. So that's the a little bit of an update. I just try to flesh it out a little bit for you. And then I added this step 2 here in initialize, which is the other thing. So you can either do it in your main before you get to the loop, or it makes a little bit more sense to put it in the initialize, because the initialize always happens once, and it happens before the main while loop. So I'll just go through it then. This is new. Additionally, initialize connector A DIO channels 1 and 2 in the usual way. So just as we did here, we had to initialize these channels. We're going to use them as outputs. Furthermore, set them to 1 and 0 respectively via DIO write bit. So we've used DIO write bit. We can use DIO write bit. We're going to use DIO write bit in our state functions as well. But we use it here to just set these bits once and initialize. And it's just going to set the direction of the motor. So this sets the motor direction via its input pins in A and in B. So if you set our output channels 1 and 2 to values 1 and 0, then we have a positive rotation. The encoder encounters it as being positive. And if you set it 0 and 1 instead of 1, 0, then it's in the negative direction. This is a hyperlink in the PDF to the motor driver manual. So it's a Pololu board, but it uses a pretty standard H-bridge circuit. So there's a lot of interesting stuff in there. It's a nice little, it's a pretty simple little spec sheet, essentially, the manual, but it gives a little bit of description of how it operates and why we need to do it this way. Okay, then initialize the encoder interface as before, see above, stop the motor, and set the initial state to low, set the clock to 0. So the same initialize as before, except for we've inserted these 2 extra pins. Okay, 2 extra pins, channels 1 and 2, are being used to just set the motor direction. So our amplifier requires that, so we needed to do that. Everything in these functions is exactly the same. Nothing's changed here. I wanted to talk for just a minute about calculating by just adding up the opcode number of cycles and the cycle time given the speed of the processor. inferring the real time from our weight functions opcodes. So I give a reference here. It's in footnote 6. So see Appendix B of the reference manual, which is shown here. And the reference manual has an appendix in it, instruction cycle timings. And I encourage you to look through this. It's not a ton of information in here, but there's a little bit of information on it. One of the things that it says is that, so unlike some simpler processors, this processor is kind of to the level of complexity. It's really hard to predict timing exactly, but you can get a pretty good approximation of it, especially if you're using only certain opcodes, certain instructions. If you're using other instructions, it gets harder and more difficult to predict. It depends on what's in the registers and the order of them, and so it's a little difficult to come up with a good approximation for this processor, but you can still approximate it. So, for instance, it lists these opcodes and approximate number of cycles. Frankly, I don't totally understand the, especially in this one, I don't totally understand this term fast forward cases versus other cases. However, something we can do when we look at this is to say, okay, LDR, so for instance we have in ours in LDR, okay, you're looking at the result latency, and we are gonna probably be in this center column for the most part. So fast forward cases, although I don't have a precise definition for that, that seems to be most of the time. So it shows up nowhere in this document other this term fast forward cases. However, this result latency seems to be the center column here seems to be the right number of cycles for these for our commands. And notice that our LDR commands, since we've got 417,000 of the LDR commands that get run twice in this, because we've got it in the while loop. It takes up a big chunk of it. I think it's like 50%. I think LDR and move, and there's one other, I think compare. These are primarily the commands that are being, or the operation codes, the opcodes that are being run in this wait function, in this while loop. So we have to get those ones right. If we get those ones right, then the other ones, I mean, we might be off by a very, very small fraction if the other ones are slightly off. But the ones that happen 417,000 times, those are the ones we really got to get right, because we're going to multiply whatever number of cycles by 417,000, and that means it's a significant chunk. So we have to get those ones right at least, and I would encourage you to use the result latency. And when you look at it on the oscilloscope, you're going to be able to see the timing, and you're going to be able to find out what that is in milliseconds. And if you're off by a tiny, tiny fraction, you probably wouldn't even notice it on the oscilloscope. But if you're off by a factor of 2, that would be an indication that you probably interpreted from this Appendix B of the reference manual for the processor, the wrong number of cycles, because you multiply that number by a large number, so that one becomes important. So, for instance, LDR you find here, and the others are also there. And pay attention to the fact that branch instructions take no cycles. It's pretty cool. So anyways, it's interesting to go through and look. Timing is difficult on these more complex processors, but we can still get pretty close. So especially if we limit the number of different opcodes we use, like we're not using very many exotic opcodes here, and no 64-bit pieces of data, which is another thing that throws in a sort of monkey wrench into the timing as well. So everything's 32-bit only, so it is pretty good, our estimate. So it I think it might be a little bit too much to ask to say the exact number of clock cycles, but we could get a really good estimate of the number of clock cycles. And you should be able to verify that on the oscilloscope. And for us, so free running, if you use the suggested 2, M is 2 and N is 5, you're going to be in the ballpark of 1500 RPM. So that is another thing to note for us. It's not exactly 1500, but that's the ballpark. Yeah, so those are the main things that I wanted to cover. Oh yeah, I did add. So in this exercise, we learned how to do PWM with this finite state machine. However, the finite state machine way that we do it requires that we use that our BTI, our basic time increment, is rather large. So we don't have a really high rate at which we're doing our PWM. And you're going to notice this when you do, if you put in like M is 2 and N is 20. It's going to be really, you're going to see that pulse happen in real time. The motor will suddenly speed and then it'll slow, and then it'll speed and it'll slow. So it's pretty jerky. That's not what we want from PWM. We want PWM to appear continuous. So as PWM, we need higher rates for like doing it the right way. Let's like say that in this section is the right way. And there is a way to do that with this board, and it's much better than the way we're doing it in that sense. But I wanted us to learn how you might do this if you had if you're programming the FPGA, which is how this board does PWM, is in the FPGA at a much higher rate. But the same issues arise even in the FPGA. It's better because you're going faster, but if you go too slow with your PWM, you're going to see the pulsing. If you have an upper limit to your resolution. So like if you're down, if you say, okay, well I'll do N is 4, and then I'll do M being 1 or 2 or 3 or 4. You don't have very much resolution in your duty cycle. You have 0, 25%, 50%, 75%, or 100% duty cycle. You don't have anything in between. So if you make N larger, you have more resolution, but your frequency, your PWM frequency goes down. Same thing happens even when you have a higher BTI, which the FPGA does. So that is something to keep in mind. So if you wanted to do PWM on this sort of the right way, you would use the FPGA's PWM capabilities, and there are C drivers that come in the C support from MyRio that allow you to program these pretty easily. So there's an example. So if you download the C support, there's an example of using PWM. I think the example uses like 10 kilohertz as a PWM rate, which is usually pretty good. You probably wouldn't notice 10 kilohertz. But it can go up to 10 megahertz. But when it goes up to 10 megahertz, I think at 10 megahertz it only has duty cycle capacity to do like, I think it's actually 0, 25%, 50%, 75%, and 100%. So as you lower the frequency, you can get better resolution in your duty cycle, but there's a limitation. So there's a trade-off there. And it's part of what we're learning in this lab is that there are these trade-offs, even when you're using the higher rate that the FPGA has. So we might still need a finite state machine for controlling the state at a higher level. So maybe we don't brew our own PWM signal in this way. We'll use the built-in functions to have the FPGA do the PWM for us. That's the better way to go. But we still might need to use finite state machines for things. So for instance, this problem could be changed just slightly. If we included a knob for controlling the duty cycle, so like we could have a knob that was maybe a potentiometer that had an analog input to the board, and that analog input was being read to determine what the duty cycle should be. So we could, the voltage across it could be read, and we would be then thinking about, okay, so if the duty cycle is this, well, we don't want to update the duty cycle at the rate of the FPGA. That would be way too fast, and we actually couldn't do it probably. So we need to do that at a lower rate. Also, we could do these other things that we're doing too, like we could have the encoder measuring the position and the speed. We could display the speed on the LCD. We could stop using the button. All of the same things we could do. It's just that instead of controlling when the signal's on and off, like creating our own PWM, we could be just updating the duty cycle of the PWM each time through. So that would be another way to go with it. Decoupling the timing processes that happen at much different rates, like this is typically advantageous. So like the FPGA, we want to do something blazing fast. We want it to go as fast as it can and do this high rate PWM for us. We don't want to hang around and wait for us to update, like what is the speed. It would be not even useful to update the speed at a rate like that. We wouldn't be able to see it on a display that fast. So recognizing these two different timings and decoupling them, in this case the PWM from the updates in the speed and maybe even updates in the duty cycle if we had so set it up, is a good thing to do. So I added this little section to describe that. I thought about switching us over to doing this problem, but I decided to keep it the way that it is because I already presented it this way. And it's still good, and we get to learn how to do the PWM ourselves, to brew it ourselves, roll our own, right? We like to do that. So that's what we're going to stick with in this lab. But I wanted to show you, if you wanted to do it sort of the right way, this is how you would do it. So, okay. That's all I've got for you. So good luck on everything. Keep me posted. I'll be around some of the breaks. So just let me know. All right. Take care, everybody.